Okay. Due to the size of this group, this needs to be very, very informal. At any time, if you have a question, stop. If you have any examples from projects you've worked on for things that remind you of things that we've talked about here that you want to elaborate, that would be great. Most of us find that the only way we learn is by our failures, okay? And unfortunately, that's true for most of us, most of the time. So I would hope that after this, you will be able to recognize some things before they turn into failures. I labeled this thing piping flow and chiller plant applications. It could even include a little bit of heat transfer. Because the one thing we all need to be is really good systems people, okay? There are all kinds of people out there that can tell you about a piece of equipment. There are lots of control companies out there that can tell you how a specific piece of equipment works in their control system. But where our value as Trane Company comes in is the ability to understand what happens to the system when you put everything together. And that comes with a lot of experience, and frankly, with Trane, we have a lot of good material that is available to us from the corporate standpoint that really helps us understand systems, okay? So, my first question is, if you love math, raise your hand. Shit. Well, we got almost half the room, that's good, okay? Now, I have to seriously question anybody that doesn't like math, because I love math, and it's fun.
Question them, Tony, question them.
Okay, we're going to start with a formula. Does anybody know what Q is here?
Heat energy.
Huh?
Heat energy.
It's heat, okay? Now the reason I'm starting with a formula here is that a lot of times you're working on things and you need to do what I call a test of reasonableness. Does this information actually make sense? And water flow is the easiest thing in the world to do tests of reasonableness on for heat transfer because it's governed by this equation. Q is BTUH. Does anybody know what 500 is? It's a thermodynamic constant that comes from years of calculations. What's GPM?
Gallons per minute.
Gallons per minute of flow. And what's DT? Temperature change, delta T, okay? That's the difference between the inlet and the outlet water. Now this formula applies to everything, okay? It can apply to a boiler, it can apply to a chiller, and it can apply to a coil you're working on, okay? So it's real easy. So, everybody got their phones? Get your phone out. Oh, I got one more formula. Who doesn't know this? Okay, I want everybody to say at the same time. 1 ton of cooling is 12,000 BTUs.
All right, we're all here.
All right. And the only reason I bring that up is because heating equipment is always rated in BTUs, but cooling equipment is always done in tons. And the difference is just a factor of 12,000. Oh, let's go pick on Travis. Travis, you said it was a BTU, right?
Yeah.
What does that stand for?
British thermal unit.
A British thermal unit. Do you remember what the definition of a British thermal unit is?
Ooh, it's the amount of energy required to convert, or no, to change it by 1 degree, I think it is.
1 pound of water, 1 degree. is a British thermal unit, okay? You don't need to know that, that's just fun stuff. Okay, you have your phones out here. I want you to assume you have a cooling coil that has 50 GPM going through it. The entering water is 42, the leaving water is 46. And how much work or how much cooling is the water doing on the air?
350,000.
Hang on a minute. I want everybody to figure it out. Everybody got their answer? Okay, now you have 4 choices here.
Should be using Menti, Tony, so people could vote on it.
Oh, I should have.
That's why I thought I was getting my phone out.
Okay, how many say it's number 1? How many say it's number 2? How many say it's number 3? How many say it's number 4? Wow, we got smart people in this room. Okay. All right, now I'm really gonna make you work your brain hard here. How many tons of cooling is that? How many say number 1? Number 2? Number 3? Number 4? I shouldn't have picked C again. This is awesome, man. You guys got the math down. Now, was that hard math? No. Okay? And that's like half of the math you need to know. It's that easy. All right. Now I want to talk about coils here for a minute. We're going to talk about 2-way valves and 3-way valves on cooling coils and how they work. All right. Coils work on a principle called LMTD, log mean temperature difference. Okay? An example is, let's say we have 42 degree entering water on this coil, and we have 80 degree entering air. Okay, in other words, the hottest versus the coldest. All right, so that means the log mean temperature difference is 80 minus 42. All right, now if I took that same coil and instead of 80 degree entering air, I had 50 degree entering air. Yes.
What's that terminology called again?
Log mean temperature difference, LMTD. If I took that same coil and instead of 80 degree entering water, or I'm sorry, 80 degree entering air, let's say I had 60 degree entering air, would that same amount of water do the same amount of cooling? Okay. Now let me teach you a trick that I use a lot of time when I'm doing logic stuff, is I always take the argument to an extreme, okay, to figure out whether it works or not. If I had 41 degree entering air and I was trying to cool it with 42 degree water, would I be able to do much cooling? No. You can't, because there isn't enough differential between them to make them work. All right? So one thing you always have to think about when you're looking at coil performance is, what is my design condition versus where it's operating at? And one of the places you guys will see this a lot is our air handlers are always designed around some amount of outside air. And usually it's in the 15 to 25% range of outside air. Now, this unit is calculated for Chicago because we normally have about 80 degree mixed air temperature when it's 95 degrees outside and we're bringing in some outside air. the temperature in the mixing box will be about 80 degrees. Now, what happens when the guy overrides the outside air damper and it's 100% open on a 95-degree day? Can you get 55-degree air off the coil? No. Coil wasn't designed for it, so you can't get it. All right? So always remember, when you're looking at coil performance, you need to find out what the design data was. Now, in the same way that if the air is too hot, the coil won't perform, let's say they have the chilled water set point at 48 degrees instead of 42. If they have 48-degree entering water on that coil, are we going to be able to make 55-degree leaving air?
Depends on degree of air.
Very good, it depends on your entering air. So let's say today it's 60 degrees outside, we can probably make it. But if it's 95 degrees outside and we have 80-degree entering air to that coil, we'll never make it. Okay, there is one very common thing that pipe fitters do with coils that screw us up. Does anybody know what it is?
Pipe them.
Sorry?
Whatever.
Bypass.
The bypass? Well, even more elementary than that. Can anybody see what'll happen? I don't have a laser, do I? When you look at this, the airflow is going this way, the water flow is going this way. Now, if you think about that, the hottest air is here, the coldest water is here. Okay? And it's designed that way for the best heat transfer. Let's say they pipe this coil backwards and they put the 42-degree water on the 95-degree side of the coil. Okay, does anybody know what happens to the coil performance?
Goes down, drops it.
It does, it goes down dramatically. And the reason being is when you pipe it this way, you have the coldest water hitting the coldest air. So therefore, you have the opportunity to get the coldest air off this coil.
Does it matter, Tony, if it's a double row or a single row coil?
No, no. And this is, you know, it can be anywhere from a 1-row coil to, you know, a 10-row coil. Now typically on chilled water coils, each pass is 1 row. In other words, they'll feed all the tubes on 1 row, send the water down, and on the back end of the coil, there'll be U-bends that turn the water around and bring it back. Okay? But if you're ever running into a job where you've got design water temperature, you know your air temperatures are okay, the water balancer told you you weren't short of water, and we can't get leaving air, man, that's the first thing I'd look on is, do they have it piped backwards? Because that is really, really common. Okay? All right, now let's look at what happens here at design conditions. And I'm just looking at the water side right now. Okay, I have 7 GPM of 42-degree water coming from down the main. Now at full design, my bypass valve is completely closed to the bypass and all the water is going through the coil. So I have 0 GPM going through the bypass, and I have 7 GPM coming out of here of 52-degree water. Does everybody follow that? Does that make sense? All right, now we're going to say that we're at a light load condition, and that bypass valve is mostly open to the bypass. What's going to happen to the bypass GPM? It's gonna go up. What's gonna happen to the GPM going through the coil? It's gonna go down. And what is gonna happen to the leaving water temperature? It's gonna go down, right, because we have cold water, okay? So in this example, if I put 1 GPM through the coil and I bypass 6 GPM, that means that my leaving water coming out of that coil is 43.5 degrees. Okay? This is extremely important when we start talking about chiller plant design and things like that, because chillers like delta T, okay? They want a big delta T to work on, and when we have a little tiny delta T, they don't work well and it's inefficient. Okay. Oh, this is a two-way valve, okay? So in this situation, we don't have a bypass pipe anymore. So at design load, what would we expect the entering water to be? 42, we're gonna have 7 GPM, right? At design load, we're gonna put 7 GPM out of the coil, and that's gonna be what temperature? 52. Okay? What happens at a light load?
The valve modulates less flow.
The valve closes,
GPM goes down.
I'm sorry?
The GPM goes down.
Yep, so when the valve closes, we're gonna have less flow through the coil. The delta T goes
Still
up.
using all the energy.
You have less flow through that coil. So that GPM is doing all the work now. So it's going to be high. Now, I made this number just because it's easy. It isn't linear like that. In other words, you won't always have design leaving air or design leaving water on a two-way valve. But you will have a much higher delta T than you will in a three-way valve. Everybody okay with that so far? All right, now we're going to get into some chilled water system design.
Hey, Tony, I have a question here.
Yeah,
On coils, why do they always have the valve on the return side?
everything is about history, okay? And it has to do with a long time ago when they made valves, they were easier to make with one inlet and one outlet. As far as pressure drop on a two-way valve, it makes virtually no difference, okay? But it all goes back to 40 years ago, everything was three-way valves. Nobody used two-way valves. And the convention was mixing or diverting valves. On a three-way valve, if it's on the inlet of the coil, it's a diverting valve. If it's on the outlet of the valve, it's called a mixing valve. And now Jake is going to come up and explain to you how you tell the difference between them.
You do it so much better.
Come on, you gotta do it. You gotta do it.
All right, I'm not coming up there.
You gotta draw it.
I gotta draw it.
You gotta draw it.
All right, fine. I only had to listen to this probably 25 times. All right, so now I'm gonna steal your terminology, is that okay?
It's not patented.
Okay, good. Yet. If you're gonna have a legacy, Tony, that needs to be it. All right, so let's say we have a mixing valve. The difference between mixing and diverting valves is the gazintas and gazatas. It's how many gazintas and gazatas.
It is a Tony.
It is a Tony. So a mixing valve is mixing two things, so it's going to have two gazintas and one gazata. So gazinta, gazinta, gazata. Somebody bless me. Diverting one gazinta, two gazetas. So it takes the gazinta and it puts it to one of two gazetas. Gazinta, gazeta, gazeta. Bam. Thanks, Tony.
Okay? And a long time ago, when
And
they
that's
were
on camera now.
when they were manufacturing these three-way valves, it became a convention to use a mixing valve rather than a diverting valve. So what happened is, from a manufacturing standpoint, mixing valves were less expensive than diverting valves because of the fact that they made more of them, okay? And they have to be built differently. You can't, back in the days of globe valves, you have to manufacture them differently. Now that we use ball valves on everything, doesn't make any difference, same piece of hardware, okay? But that's why, and so they were always mixing valves, they were always on the leaving side. So when we started moving to two-way valves, it was just a convention to put them there.
To me, it's always been an identification, you know, kind of, it's always on a return. Not that the fitter would put it on the wrong one, but it's a general rule of thumb, you see a valve there, you know, that's your return side supply.
That has been an industry standard,
Right.
but
But it would help these guys to identify when you're talking about, you know, supply return,
yep.
kind of identify it that way. I mean, check the pipe, make sure it is really true, because you can have a fitter out there that can put it in the wrong spot. Absolutely.
And the main place you really, really need to be careful about these is in large hydronic systems when you have like a reset valve, but it's a butterfly valve, or it's a big, you know, two valves that are linked together on a T. And that becomes very important how they pipe it. Okay, thanks, Kevin. All right, when we start talking about system flow, you need to know what the devices out in the piping are, okay? Because if you don't know whether those air handlers have two-way valves or three-way valves, you're not going to know how your central system is going to need to operate, okay? And we'll go through some examples later. Now, this is a very, very simple system. I have one chiller, I have one pump, I have two coils, and I have two three-way valves. This is the simplest chilled water system that you can make, all right? Let's back up here for a minute. For the last 50 years, this was the way most systems were built. Can anybody tell me why this is not a good system to put in? What's wrong with it?
No redundancy.
Hmm?
No redundancy or.
Okay, well, I'm saying, okay, at this point though, all they could afford was one chiller, they couldn't do redundant chillers.
It's because you're not being able to you're varying the flow through the machine.
Well, that's actually constant flow through the machine. Does everybody see
Because
that?
you won't have constant flow out in the field because of the valves. Well, you will because it's not on.
No. All system design changes that have happened in the last 40 years have all happened for energy reasons, okay? We're trying to make systems more efficient, okay? And the first thing you see is we're pumping a lot of water all the time, whether we need it or not, okay? The same reason that we have VAV air systems is the same reason that we have variable flow pumping systems. It's not because they're intrinsically better, it's because we can save energy in operating them. So this is a simple system.
How much, hey Tony, how much energy do you actually save when you're varying a VFD? Is there a calculation, you know, like 10% of a VFD saves X amount or something like that?
If you are talking about a given system, in other words, so many GPM and so many feet of head, and you can change the speed of it, there's a thing called the fan law, which applies to pumping systems, okay? let's say you have a rooftop running and you change the RPM of the fan by 10%. Let's say the system's the same, you raise the RPM of the fan 10%. You've got enough motor, everything's fine. Does anybody know how much more air you will get out of the unit? The fan law says that if you raise the fan RPM 10%, you will get 10% more air. Okay? Then the next thing is how much more static pressure will it take to do that? Okay? To raise it 10%, that's a square relationship. So that means it'll be 1.1 times 1.1, or 121% as much static pressure. Okay? So I'm operating a rooftop unit at 10,000 CFM, everything's at steady state. Somebody says, I want 11,000 CFM. Well, whatever static that thing was operating at before, it's gonna have to be 120% of that static to deliver that air. That's the square relationship between static pressure and RPM. But the kicker is the horsepower relationship. The horsepower relationship varies with the cube of the change. So it's another 10% times 120, okay? So in a VAB system, if we can reduce the CFM 10%, you're going, what's 10%? That's nothing. But at 10% reduction in CFM, you're only using 60%, 65% of the horsepower you were using at 100. Okay? And that works for water and air.
So it's a pretty substantial
Yes.
savings when you drop a pound or two.
Sure, yeah. So that relationship between flow and horsepower is what drives VAV systems and variable flow pumping systems. Okay? All right, this is a very simple system. Now, the thing that happened after we had 1 chiller jobs was we came up with 2 chiller jobs, okay? And we needed a way to control the system. Now, I don't know if you can tell, the top chiller is supposed to be a small chiller. The bottom chiller is supposed to be a big centrifugal, so these are not equal-sized chillers. Now, is the pump on the little chiller constant volume or variable volume? Here, we'll just go around the room. We'll start with you. Is the pump on the little chiller constant volume or variable volume?
Constant volume.
It's constant volume. How do you know that? Because it says CV. Okay, you get the next hardest one. What's the centrifugal pump?
Constant volume.
Okay. What's the system pump down at the bottom?
Variable volume.
It's variable volume. Okay, very good. Now, again, this is really going to be difficult. We're going to do some math here. Okay? I have a constant volume pump on the top moving 200 GPM. I have a constant volume on the top at 700 GPM. What is the flow in the bypass?
It depends on the size of the bypass.
You don't have enough information to know that. I love trick questions. Okay, now, the pump down on the bottom is now moving 600 GPM. What is, now does everybody see that we have 2 loops going here that are completely independent? Regardless of what is going on down here, this pump always has a path to get water, okay? so it can move as much water as it needs. This pump down here has a path through this bypass, so it can get as much water as it wants to handle. So, what is the flow in that bypass pipe right now? Which way is it going?
That's a question.
No, it's absolutely not a trick question.
It's going right to left.
It's going right to left, okay? Now, does everybody see that? At this point right here, I have 700 GPM that has to go somewhere. By the way, water is not compressible, okay? So I can't have different things happening in the same system. So I have 700 GPM entering this T here, okay? And I have 600 GPM going out this port of this T. So that means there has to be 100 GPM going across that way. This thing is called a decoupler, and it allows water to move back and forth depending on the system load. Now, we've got another example here. Now, the load in the building went way up. Okay, we turned on some air handlers, whatever. And now we're using 1,000 GPM down there. Okay? How much flow is there and which way is it going?
300 GPM. Not sure.
Okay? Okay. Now, this was the way centrifugal plants were built 40 years ago. Okay? And the reason is that down at the bottom there, you see we've got two-way valves and VFDs. So we're saving energy there, right? I mean, we're only using as much water as we need, and that's called the distribution loop. But up in the top part, we're still running both those pumps at design GPM all the time. And that's wasting energy. So this is what's called a variable primary system. In a variable primary system, the pump handles the water throughout the whole system. All right? Let's back up and let me give you something here. Does anybody know what a pump efficiency is? In other words, anytime you're dealing with a pump or a fan, you're putting electrical energy in and you're getting mechanical energy out. Okay? On a pump, do you know for the electrical energy you put in, how much output you get? Anybody ever seen a pump curve?
Yeah, you can see horsepower versus.
Yeah. What kind of efficiency can you expect? Oh, okay. I thought I'd seen it.
No, I've seen those.
Typically, pumps are no more than 60 to 70% efficient. All right? So that means the energy I'm putting into this pump, I'm getting about 70% out of it in flow here. And then I grab that same water with another pump and I do some more work on it. I move it again. So that means these pump inefficiencies are added. So my system efficiency goes down the more often I run it through a pump, because pumps aren't 100% efficient. Okay, and this is a variable primary system, and you notice here, the pump has to get the water, push it through the chiller, send it all the way out to the loads, and bring it back. So that means that when you have primary, secondary pumping here, these pumps on the chillers, all they have to do is get the water out of the chiller, through the bypass line and back to the chiller. So these are typically pretty low head pumps, okay? That pump there has to take it from the chiller plant, send it through the piping all the way to the far end of the building and then suck it all the way back, okay? So when we have a system like this, a variable primary system, this pump has to do both of those jobs. In other words, it has to get it through the chiller, it's got to send it out to the building, and it's got to get it all the way back. So on a variable primary system, your pump heads will be higher than a primary secondary, than either one of them individually, but it's more efficient. Okay, is this a variable flow system? No, it's not. That's constant flow. Now in primary, secondary, it looks like this. Now, is the primary side of this system constant flow or variable flow? And it's a trick question.
Two-speed.
Who said that? It is constant flow, but it's two different constant flows, depending on whether you're running either chiller.
High and low.
Okay, is the secondary side of this system constant flow or variable flow? Is it variable or constant? How many say variable? How many say constant? Okay, you see what I put on that thing?
I got Travis's head in my way.
He was hiding the bypass.
He was hiding the bypass on the coil? Okay. I added a three-way valve down there to make that a trick question. That's really constant flow because, again, there's a three-way valve. So, we got a VFD out there. Is the VFD gonna do anything? No, it's gonna sit there at constant speed all the time because it's a constant flow system. By the way, does anybody know why you use VFDs on constant flow systems?
Balancing?
I'm sorry?
Balancing?
Balancing, that's a very good one. Yes, you can use it for a balancing. Yep.
And motor starters are really loud when they get old.
So what are you saying?
Soft starts.
Soft start, yeah. A VFD will bring a motor up to speed more slowly. It's not as much of a shock to the system. Okay, now, I took the three-way valve out. Now, is the secondary side of this constant flow or variable flow? Now it's variable flow, that's right. Okay, now when we start talking about variable primary flow, there are two major new control items that we have to introduce. One of them is the minimum flow bypass valve. Why do we have a bypass valve? Okay, so the chillers can get their minimum flow. Why does the chiller care? Okay, it won't run without minimum flow. Why don't we let chillers go down to zero flow?
It's not doing any work.
Well, it's not doing any work. Okay. you
Turn off
get-
the high head, right?
Well, not high head, but low suction.
Well,
Yeah. The thing is you have to remember that in a chiller, we have this big pool of liquid refrigerant that is boiling off in the evaporator. The hot water comes in and boils off the refrigerant, okay? And if we don't have water coming through, that refrigerant is going to boil off, and it's going to really cool the water a lot, okay? And what happens is the temperature goes down and down and down until the chiller makes solid water. You guys know what solid water is? That's ice, okay? You never ever want to make solid water with a chiller, because that will be very expensive.
It expands.
It expands, yes it does, and it's very, very bad. Somebody asked me once, well, why didn't we do variable flow, 25 years ago? Well, back then, chillers had a big pneumatic operator that operated the inlet vanes on them, and that was your control system, okay? Extremely inaccurate. The only thing it did was make leaving water temperature. It didn't know anything else about the machine, what the refrigerant temperatures were and all of that. So the reason we never did variable flow a long time ago was the equipment simply couldn't handle it, okay? With the starting out of the first electronic controls and then full DDC controls on chillers, they can now manage the loading of the machine so that it doesn't have problems. Okay, so we have a bypass valve, and its job is to maintain minimum flow. Does it have anything to do with temperatures? You open and close the valve based on temperatures?
No.
No. It has one job in life. What do we control a bypass valve from? From the chiller
To the chiller.
to the chiller.
What do you mean, what is it controlled from?
How do we make a decision on whether to open or close that valve?
Oh,
Yeah, so we measure the flow going into the chiller.
Okay,
supply and return.
okay,
DP, differential pressure.
okay. So you set a flow meter.
Yeah.
Okay, so we could put a flow meter on each chiller, and we would get some information from the vendor of the chiller on what their minimum flow is, and we could maintain that. Now, does anybody know whether flow meters are high or low cost?
Major high.
Major high. Flow meters are expensive. Okay? So, we're always looking for a less expensive alternative.
Cheap.
DPs are less expensive, okay? Now, one of the things we have to be very careful of is, and the good thing is you guys don't need to worry about this, it's only Jake's problem, okay? Is that you don't want to use chiller. Have you guys seen, anybody know what a traditional centrifugal chiller at minimum flow, what kind of DP it'll have?
Very low.
It's very low. It's usually, it's never more than 2 pounds. A lot of times it's a pound, okay, which is very low. Now, if we put a 0 to 100 pound transducer on that thing, how well is it gonna work when we're trying to control at 1 pound?
It sucks.
It sucks.
0 to 50 sucked.
And 0 to 50 cents, right? So traditionally, we want to, we're a little bit stuck here because we don't want that transducer to fail when we're at design flow, okay? But it has to operate at minimum flow, okay? You guys don't need to go through the sizing on that, but just, I've seen this on jobs where we go in for a retrofit that somebody else put the controls on it, and, they've got a 50 or 100 pound transducer trying to control it, pound and a half.
What's gotten a lot better, Tony, now that we've got the digital, it shows it where when we had the mechanical before, that was just rough, so we just.
Well, the mechanical
Would
one too,
opening
the pipe
the
would
bypass
crank
valve
down.
raise the delta T?
It would flood it.
With opening the bypass valve, well, we're gonna get into that in a second, okay? All right, let's hang on a second. Yep.
Yeah. That's why this new Sentinel one is a lot better, because they don't have that opportunity to flood the transducer anymore.
Well, it's also better because you can see it. There's a display right there. You
Yeah.
can see where before it was kind of a mystery.
You didn't know.
Was it
Yeah.
right?
Okay, the other new major control item is the VFD on the pumps. Why do we have a pump VFD?
To vary flow.
Okay, and why do we want to vary the flow?
Based on what the system's asking for.
Okay, we've got two-way valves out there on the coils. The amount of cooling that's needed out there in the system is going to change depending on the positions of the valves. And that's traditionally controlled from a DP. And does anybody know where the DP goes?
Two-thirds down the system.
2/3 of the way down the system. Now, does anybody know why it's 2/3 of the way down the system? That's another history lesson.
Most of you don't start.
Just because it seems to work pretty good there.
Really?
Yeah.
Seriously?
Yeah. I want you to look at this. If we put the DP right on this side of the bypass, in other words, right here, and there's no loads out here, this DP isn't going to change much as it happens out here. So you might say, Tony, let's take your argument to extreme like you do. What happens if I put the DP across the last piece of equipment? Well, it'll only vary flow as that one valve changes. Okay? So a long time ago, somebody said about 2/3 of the way seems to work pretty good. So that's what you control that on. So now, we have manifolded pumps now. Now this is getting into chiller sequencing now. Okay, when we're talking about the chiller sequencing application program and how it works. The first thing that becomes extremely important is the location of your temperature sensors. Okay? Now I'm showing it with a supply air temperature here and a return temperature here. What happens if I put the return temperature over here?
It's not gonna be true return temperature sensor.
Why not?
Because it's before the bypass.
Right. So what's going to happen when that bypass is open? It's when this bypass is open and the water's going through here, this temperature is going to be colder, which really tells me there's less load on this plant. If I put it here, it's going to be significantly warmer, and that's going to tell the plant I have a big load on me. Okay? Now, the supply temperature I'm showing on this side of the bypass, and in a variable primary system, it doesn't make any difference. It could be here or here, because water flow is always that way. What becomes extremely important is if you have a primary-secondary system, and this is a decoupler line, what can happen is when this load goes up, you're going to have water coming backwards through here, and this, you could be making 42-degree water with the chillers, and this might be 48-degree water going out to the system. And you won't be cooling the system enough. So especially on a primary-secondary system, this sensor always has to be on the other side, on the far side of the bypass, and the return has to be on the close side of the bypass. And if you don't put those in right, chiller plant control won't work because it's not sensing the actual delta T that the system needs.
Same laws can apply to a hot water system, right?
Okay. Yep.
Is that why KJWW puts 4 sensors on those systems?
Well, first of all, if you have a system like this, you should never put 4 sensors on it. But KJ would put 8 on because they want redundant ones on each one. On this system,
PAOs.
They've crossed the chillers, across, yeah.
this water, and this water should always be the same temperature. Okay? If they're not, you've got a problem with your sensors. Now, this side of the system, you could put another sensor over here, and you could see what the system return is versus what the chiller plant is seeing because of the bypass. But again, if this valve is closed, these temperatures should be the same all the time.
Could we get away with not putting a chill water supply and a system supply? Would that still meet their spec, or do you have to put both sensors in?
Say it again.
KJWW, if they come and tell you you need chill water supply, a system, and.
We put them in.
We put them in, so,
Put 'em in.
okay.
Yep.
I was gonna say, because.
You can't use logic. You guys should know this. You can't use logic in dealing with an engineer. Okay? You just have to do it the way he says.
It's like wrestling with a pig.
That's right.
In the mud.
Which feels acceptable, it's good range, that depends on the system.
It does. And we're gonna get into that.
Okay.
Okay. So. Okay, what we're gonna do is, we're gonna walk through a scenario here where we're gonna start up a chiller plant. And we need to talk about the sequence in which we do things, because this is very important. Okay? So we're gonna start here, everything's off. Now, does anybody see a problem with any of this? The chillers are off, the ISO valves are off, the pumps are off, pump speed is at minimum, and the minimum bypass valve is open.
I would think the bypass valve should be closed.
Okay?
So when you start it up, you'll have flow through the chiller.
Oh, wait a minute.
No, I think the valve should be
If the
open.
bypass valve is closed,
Bypass valve should be open until the chiller valve opens.
Okay.
If the bypass-
Okay, never mind.
but you're bringing up the point I wanted to bring up, and that is the most important thing in variable primary flow is keeping the chillers happy, okay? That is absolutely the most important thing. So we always start up with the bypass valve open,
You're right.
and then if we have flow through the chillers, we can close it and push water the other way.
You always want to keep max through the chillers to start up.
Yeah, yeah. Okay, now, I meant to put another slide in here, I didn't. Okay. So when we start our first chiller, the first thing we're gonna do is open the chiller isolation valve. Does anybody know why we open the valve before we turn on the pump?
You don't want to deaden the pump.
You don't want to deadhead the pump. Does it damage a pump to deadhead it?
After time, yes.
Excellent point. After time. It doesn't kill the pump to do it for 30 seconds or something like that. And if somebody tells you-
Centrifugal pump.
You're a centrifugal pump, yes.
Yeah. Positive displacement could be an issue.
Well, we don't have any positive
But it could
displacement.
be an issue.
We don't have any gear-driven water pumps that I know of. So the idea is you always want to make sure you have a path for the water before you turn on the pump. So you open the valve, you enable the pump, you let the chiller prove its flow, and then with our standard is we try to put 2 proofs of flow on the evaporators on all our chillers, okay? And what that means is the IFM, everybody know what an IFM is?
No.
Okay, an IFM is, do you remember that? It's something flow monitor. It's an electronic device that you
infrared,
stick in the pipe.
Isn't it infrared?
No, it's not infrared. You find that.
Nice guess, Jake.
Jeez.
I actually thought it was.
I don't think so. But it's a vendor that Trane Company is using that they use for their low flow protection on their chillers. Okay, so we used to use DPs and paddle switches. Both of those have issues with them. Neither one is good and neither one is bad. But what we do is we use the IFM on the machine. Now that's wired to the controller, so the machine can't start unless that's there. Then we use a secondary proof of flow. And the secondary proof of flow is typically an end switch on the valve. Okay? So we won't let the chiller start until the valve gets to its 100% open position and the IFM makes, okay? So once we've got both of those done, the unit will start up the compressor. And at that point, the pump maintains the system VFDs. So that means the only thing that controls the speed of those pumps are these DPTs out in the system. Everybody see that? And that is so critical because people keep wanting to try to mix, well, change the speed of the pump because of this. No, the speed of the pump has to maintain the DP out there. All right. Now what happens if our load drops and this bypass opens up? Okay? Let's say we're running along, this valve is closed, everybody's happy. And somebody turns off a gigantic air handler out in the system. And the valve on that air handler goes closed. Okay? Suddenly, our GPM is going to go way down, right? Now, when this GPM goes down, what's going to happen?
Your DP will go down.
This DP will go down, but more importantly, the first thing this needs to do is protect the chiller. So this valve has to open. Okay? Now, what happens when you open this valve out here? What happens to this DP?
It's gonna drop.
Does everybody see that? It's going to drop. Because suddenly water that was available out here is now short-circuiting back to the return.
And you really don't care what's out in the load, because you gotta protect that machine.
And that's exactly right. You don't care what's going on out here. But it is really important that this thing work.
Because if it drops out, you got like 20 minutes, you gotta wait for it to restart again.
Yeah, different chillers have different anti-recycle times on them. And most of our chillers, if they've been running 30 minutes and you lose flow, they'll start up immediately. But if they just started and you lose flow, you might be out for 20 minutes and there's nothing you can do to get that chiller online.
And what I've done with that bypass valve that Tony talks about, you have two
No.
DEC loops.
Hang on, don't go there yet.
Sorry,
Okay,
I apologize.
we're gonna get there. Okay, now, the system's running on low load, we got one chiller running, everything's fine, okay? Now what happens when we want to bring on a second chiller? What do we do first?
Isolation valve opens.
Okay, now, we're going to make this real easy. These are 1,000-ton chillers. They have a minimum flow of 600 GPM on them, okay? This guy's running at 800 GPM. For some reason, somebody decides to turn on a chiller. This pump is moving 800 GPM right now. When I open that valve, what happens? Suddenly, I split this flow from 800 GPM and gave it 2 paths. So immediately what's going to happen is I'm going to have 400 GPM going through this chiller, okay? And chances are very good it may experience a flow loss, okay? Because you just drop the GPM on it really quick, and you don't want to do that. So as the load increases, the DP, we're looking at it operating with one chiller right now. As the load increases, valves are going to open, the DP in the system's going to go down, and the pump speed will increase. Okay? So that's just with one chiller running. When we want to bring the second chiller on, we always turn on another pump first. Okay? Always err on too much flow rather than not enough flow. So we open the isolation valve, we prove flow, Approve the end switch, start the compressor, and the bypass will maintain the minimum flow. Do the chillers have to have the same minimum flow set point?
No.
No. As long as you have DPs on each chiller, you can have different minimum flow set points for different chillers. And what you're going to be doing is you're running a DDC loop for each chiller for minimum flow. Now, if the chiller is disabled, you obviously don't run that loop, okay? But for all the chillers that are enabled, you have a DDC loop running for minimum flow. And whoever wants that bypass valve open the most always wins. Okay, so if one of them wants it 10% open and one wants it 25% open, you open it 25% because you gotta maintain the minimum flow in the critical chiller. What turns on a chiller, what turns off a chiller? Chiller plant control. What turns on a pump, what turns off a pump? Okay, can I run one chiller with two pumps? What's that?
You can, but waste would be a waste.
Might not be. You might need it, okay?
He said the turn pumped out before you turn your chiller on, so you would need to.
Can I run two chillers and one pump?
As long as that pump is inside the minimum flow on both
Maybe,
chillers.
yeah. Yeah. So, the reason I bring this up is, it's not, yes, you always have to do this to either one of those. Okay? Now, we get to use our math brains again. The system is designed at a 16-degree delta T and 1,000 GPM on each machine. Now, the coils, for some reason, are producing a low delta T. Can I operate at 2,000 GPM and an 8-degree delta T? Okay? The system is designed, that chiller can handle 1,000 GPM and do 16 degrees worth of work. Well, if the load out there is only 8 degrees, can I then change the GPM to 2,000 GPM and the chiller will work?
Where do you get 8 degrees from?
I just made it up.
It's like 8 degrees in the system, correct?
Yeah, 8 degrees for the chiller.
For the chiller.
Okay. In other words, what I'm saying here is, this chiller is designed at 1,000 GPM, it leaves, goes out here at 42 and comes back at 58, 16 degrees.
Okay.
Okay? So that's what it's designed for. Now, if something happens out here, and instead of needing 1,000 GPM at 16 degrees, it needs 2,000 GPM at 8 degrees, can I run that machine?
It works out to be the same.
Huh?
So it works out to be the same.
It works out to be the same. Now, how many of you have been to Albany's Candy? Okay? This is how Albany's operates. Okay? And the reason it operates that way is the way they operate their air handlers. And they always leave the coil valves wide open at the air handlers. And we have what's called low delta T syndrome out there. So what happens is we're sending cold water out at, I don't know, 38 degrees or something, and it comes back at 42 or 43 degrees. So it's very low delta T on the system. But the real cool thing is, those chillers are kicking butt and taking names because they're running up at about 1800 GPM at a low delta T, okay? So you have to look at what both sides of the system are to understand how it's operating. All right, now let's look at a decreasing load right now, okay? What are we at, one chiller running? Well, obviously, we're just gonna shut things down. I think I screwed up my slide. This was supposed to be, oh, this is after the change, okay? If you were running 2 compressors here, 2 chillers, and you decide to shut down a chiller, you wait for the compressor to stop on the second chiller, then you close the isolation valve, and then if you're gonna do something with the pumps, then you would disable the pump, okay? The bypass valve is going to maintain the DP out there for the running machine. But the real problem we always have with chiller plant control is starting the lag machine. Because if you don't have enough water flow through the pump, or your valves operate too quickly, you end up splitting that flow and you lose them on the chiller on a flow loss. Okay, the tricky parts. The bypass valve control and the isolation valve control. Those are the 2 things we have to spend a lot